Hey everybody, and welcome back to Calc 3 Online. So the plan for today is actually just do a few more examples with polar coordinates, but I wanted to start with this one. So this is just another example of one that you would want to reverse the order of integration on before you go and solve the thing. And the reason you'd want to is because, it's much easier to do an integral of dy because there's just a y there, versus dealing with this whole big messy thing. So just as this isn't a polar problem, but this is just a rectangular kind of coordinates problem that you can do really nicely if you just switch the order of integration. So to start off, I'm just going to sketch this thing. So we know on the lower bound, x is y over 2, right? So 2x is y. So we got 1, 2, we got that point, kind of goes like that. And then that's actually the lower bound, right? They're the left bound for x. And then we go up to x equals 1, which is right there. And y goes 0 to 2. So what that basically means is we're graphing, or we're integrating over that triangular spot right there. And so if we switch this thing and do if we do y cosine x cubed minus 1 dy dx, okay, y is going to run on the bottom from 0 up to this line right here, which is 2x, right? And then x would just run 0 to 1. And that's going to be a much easier problem and give us the same answer. So when we do the y integral, right, we'll just get y squared over 2. So I'm going to take a half out, 0, 1, y squared cosine x cubed minus 1 dx. And I have to evaluate that from 0 to 2x. 2x being plugged into y, we're going to get 4, and then we could divide it by 2, we're going to get 2. So we have I'll just put the 2 in here. We have a 2x squared cosine x cubed minus 1 dx from 0 to 1. And that's just a nice u sub, do u equals x cubed minus 1, du is 3x squared just 3x squared. And then that means that a third du is x squared dx, and that's the thing I can get in here, right? So I can basically switch this to a u integral, and I'll have like a 2/3. I can just pull that out. And then x squared dx du, the third is in here. And then I just literally would simplify all this to just cosine u. So I'm going to take the integral of cosine u du, and that's going to be, let's see, 2/3 just sine u, but u is x cubed minus 1, and then go from 0 to 1 in x, and so I get 2/3 times 1 minus 1 is 0, so I don't need to worry about that, so I really just have minus sine of -1. And there's an identity that minus sine of x, well, I'll just do it like this. Sine of -x is negative sine of x. So if I do that, I can kill this negative. So the final answer could just be written as 2/3 sine of 1. But that's a nice one to kind of just see how we can do that changing of order of integration, which is a very good technique to know how to do. Definitely way easier than trying to do dx dy here. Much easier to do dy dx. All right. So one of the kind of other things that I just wanted to show you right now before we get into some examples with polar again is just kind of this conceptual idea. So we talked about if we have an integral from like a to b of just like dx, then this is truly just the length of, the interval from a to b. So when you do integrals of like, if you have like a 1 in here, that is like, instead of an area problem that you're kind of used to, it's really a one-dimensional kind of area problem. And if we do a double integral, and this is really a 1 in here, because this is just like dA, right? So this is just like a double integral of dA. So this is not volume, which it typically is. It's actually just going to be area. And if you look at what it's saying R runs from 0 to A, and then the angle goes 0 to 2 pi, right? So if you draw it out, right, you go 0 to 2 pi, and your radius everywhere is 0 to A, right? And so if you just wanted to like conceptually solve this problem, you can just think of it as literally like pi r squared, area of a circle, but the r is a. So the answer to this would just be pi a squared. That would be how we can like interpret the answer to that integral. All right. So for this this problem, there's kind of a different reason I would use polar here. Another thing that you might bump into a lot is if you ever see x squared plus y squared in a problem, you might want to think about switching it to polar because, we have like this trig identity, not really a trig identity, but like just like equation of a circle, I guess. X squared plus y squared equals r squared. And so if you literally plug in r cos here and r sine here, you would see that this thing simplifies all the way to r squared. And so another reason I might want to do polar is because I see that in a problem and I know that it's going to make things a little bit easier, okay? It asks you to integrate over R2, like the full, two-dimensional plane, literally. It's just R2. And in polar, right, R2, like typically we, kind of think of like circles kind of as our coordinate axis now. But the radius just goes out to infinity, right? And the angle would be a full 2 pi, right? And so I guess you can kind of put it like that. And so if I set up bounds like with that, I would still get all of R2, but I get it with polar instead of rectangular. And that's kind of the idea here. So I'm going to go switch this thing to polar. And so we're going to do, the radius is running from 0 to infinity. And then the angle is 0 to 2 pi. And then we just have e to the negative 10, now just r squared, right? And then we have to do, instead of dx dy, we have to have our r dr d theta, okay? And this is a nice, u sub problem. If you just do u equals r squared, du is 2r dr. And then you have an RDR, so just divide by 2. And now we can go and plug things in. We'll just do that. So we got e to the minus 10 u. And then we have, so we have a 1/2. I'll just stick it there. And then du. And this thing is a nice integral, right? It's just like you would just do, right, e to the minus 10 u again, but then you would divide by the negative 10. And so we would basically just do 1 over negative 20. And then we have e to the minus 10u, but u is r squared, right? And then we have this going from 0 to infinity, and then we have just d theta left over, and theta is running 0 to 2 pi. And so then if we evaluate that thing, if we plug in 0 here, this is 1, right? And then if you plug in infinity, right, you basically just get 0, right? Because this is getting increasingly large, and so this thing's going to get real small. And so, kind of running out of room here, but we got 0 to 2 pi. We got a 1 over negative 20, stick around. And then basically we're doing, e to the infinity, negative infinity is 0. And then we do minus e to the 0, and that's just the 1. And then d theta. And so we get 0 to 2 pi, 1/20th d theta. So we just literally tack on a theta there. And so we go 1/20th theta running from 0 to 2 pi. And so if you just go and solve that thing, you would get pi over 10. But yeah, so the point of this problem, though, is to show you, I guess, two things. One, sometimes when you see x squared plus y squared, you might want to just think polar, because it's going to simplify really nice because of that. And then, put that in parentheses. And then another thing that's kind of good to see here is, if you want to describe R2 with polar, you have to use these bounds, right? Because you have to say, infinite radius, and you need the full 2 pi to go around. So if you imagine this infinite line, ray, I guess, and then you span that, or you spin that ray around, right, 2 pi, you would get R2. So that's another good part of this problem. All right, so this one is just another polar problem, and it's kind of uses a bit of a weird trick, which I kind of like. So I'm going to start and just sketch kind of the region that we're in, basically. So we have 0 to x and 1 to 2, so dy dx. And so I'm going to just sketch this here. And so we got y equals x right there. And we got 0 down here, right? Y equals 0. And then we're going to go 1, 2, 3. I think that's enough. 1, 2, 3. And we're going from 1 to 2, right, in x. So basically we get this kind of trapezoid sort of looking shape. That's my region that I'm integrating over. That's in the xy plane. And it's another one where, because you have x squared plus y squared, it might be nice to do a polar switch, because then that whole part there would just be y squared, which is going to be nice. And then also we have a 3/2. So really it would simplify to just r cubed, which is nice. But we need to figure out what this region is with basically polar. It's kind of a weird thing to describe. So the angle probably is not too hard to see. Because this is the line y equals x, right, smack dab in the middle in the first quadrant, we would see that angle is pi over 4. So we need to go from 0 to pi over 4 for the angle. The part that's a little trickier is the radius, right? Like if you think of this as the radius, you're sort of always going from this line out to this line. And so we need to think about converting those lines. So let's just take this one. This is x equals 1. And if we convert it, we would then have r cosine theta equals 1. So r would be 1 over cosine theta, which is just secant theta. And likewise, if you do this one, you would just have, x equals 2. And then you can do the same kind of math and you'll get r equals 2 secant theta. Don't know if you knew this, but secants are, if you have like r equals secant of something, then you get a vertical line like this. And so those are actually my two bounds for r. So I'm going to go from the x equals 1 vertical line to the x equals 2 vertical line. And so that should give me everything I need to go and convert this to polar with like a polar setup. So 0 to pi over 4, secant theta to 2 secant theta. And then I have 1 over x squared plus y squared is r squared. And I have a 3/2 in there, right? And then I have an r dr d theta for my dy dx conversion. So, the 2's here cancel. And so I got r cubed, but then I have this other one right here, right? So really, the problem simplifies to this. Yeah. Okay. And then, this is honestly a pretty nice integral, right? 1 over r squared. You can think of it as r to the -2 if you want. And so then it would like raise to r to the -1, and you divide by -1. So this thing is just 0 pi over 4, -1 over r, and then you'll have to plug in those secants. And if you plug those in, you will get, I'm going to switch this for a second. So once I plug those in, now my theta integral would be -1 over 2 secant theta, plus 1 over secant theta, d theta. And if you've got secants on the bottom, you could actually convert that to cosines. You could like go back to cosines, right? So you got minus cosine theta over 2 plus cosine theta d theta. And then those are really nice integrals. I'm just going to let you finish that part right there. But you should get root 2 over 4 once you plug everything in. So I think the setup on this one's kind of neat. Don't know if you knew that vertical lines were actually secants. If you literally go to like Desmos or something and plug in r equals secant theta, it truly will give you a vertical line. This is another one that I think looks really scary at first with all these square roots, but then you realize what it's saying, it's actually a lot nicer. If you go and graph this thing, okay, x equals the positive square root of 1 minus y squared is just the right half of the circle, right, with a radius of 1. And so we have that kind of region out to 1 there. I guess -1. And then, the x is going from 0 over to that. And so this is like literally what I'm integrating over. And so it's a really nice one, again, to switch to just polar. And so if you switch this thing over, you're going to get, you can see the angle runs from -pi over 2 to pi over 2. And then you can see you go from a 0 radius out to the circle, which has radius 1, which literally is just 0 to 1 then, right? And so then you have square root of r squared in there, and then an r dr d theta. And so this thing that looks really scary just actually simplifies to, I guess I'll just copy that part over for right now. You would have square root of r squared is r, then r times r is r squared, and so you have r squared dr d theta. So this is a much easier, basically problem to do, right? And this is a good one too. You can honestly think of these, so there's no theta dependence with this integral. So you can literally just do like the theta one first, honestly, if you want it, and just multiply it by it. So you can actually do this if you want, if you ever run into something like this. You couldn't do in the last one because to do the R integral, you got some theta stuff here that you had to deal with before you do the theta integral. But this one, you're never going to get that, right? So you can literally just do this as the theta integral would just be pi, you're just going to get theta, and then you're going to do, when you evaluate it, you'll do pi over 2 minus negative pi over 2. And then the R integral, you could just do, like separately, like that. And so you'll basically just scale your R integral by pi to get the final answer, like that. And so when you do the R integral, you'll get R cubed over 3 from 0 to 1. And so you can see you get just pi over 3 on this thing. So that's a good kind of trick to do. If this inner integral has no theta dependence, or it's true for dx and dy too. Like if you had a pure dx integral in here, and there was no y's up here or in here, you could do that first and then just multiply it by dy. That's like a fine thing to do. All right, so I wanted to do one more problem, and this one is kind of weird, and I'm basically actually going to ask you to prove this thing. So this is actually true that if you do, this is a single variable integral, right? If you square the integral from negative infinity to infinity of e to the negative x squared dx, you square it, you get pi, which is kind of weird, okay? And there's a reason I would want you to start with this, and I think you'll see it once we get going. But this is what we're actually being asked to do. So we're going to show that this thing squared is pi. All right, so to start off, if we're integrating over r squared, we're going to switch it into, so this is like a polar r here. So I'm going to switch this, we did these bounds before, 0 to 2 pi, and then 0 to infinity, e to the negative r squared r dr d theta, right? And then, honestly, I could use what I did in the previous problem. So we don't have any theta dependence here, right? So we really can just do like 2 pi times 0 to infinity e to the minus r squared r dr d theta, just because, you'll do an integral from 0 to 2 pi of like 1 d theta, so you'll get like 2 pi minus 0, right? So that's what I'm using to get this. I want to give myself room though. And then this thing, I would just do a u sub. So do u equals negative r squared, du equals negative 2r dr. And I have r dr, so I'm going to do du over negative 2 is r dr. And then I can go and do my u integral. So I'm going to do, I'll have this 2 pi out in front times the integral of e to the u, and then du over negative 2. So we would get basically negative pi, and then times the integral of e to the u is just e to the u, right? So I'm going to have e to the u is negative r squared, and then I have to evaluate that from 0 to infinity. And so I get negative pi, and then e to the negative infinity is 0, right? Minus e to the 0 is 1. So this thing is pi, right? So I just showed that if you do this double integral, you get pi. Okay, that means that, in terms of rectangular coordinates, right, if I do negative infinity negative infinity, e to the negative x squared minus y squared dy dx, let's say, that thing has to be pi, right? Because this in polar is this in rectangular coordinates, right? So this equaling pi means that this has to be pi. Now this is where you kind of need to, well, not quite yet actually. So I'm going to, I can think of this as multiplication of, because I can add the exponents, I can actually think of this as e to the negative x squared times e to the negative y squared, right? So I can split it into kind of an x term and a y term. And then if we use the same thing I did here, right, where I kind of just pulled out one integral, I really have the ability to do that here as well. So I can think of these as sort of multiplications of integrals. We have e to the negative x squared dx1 multiplied by this integral e to the negative y squared d1. And so those are, basically I've just done the trick where one of them is dependent on just x and one of them is dependent on just y, so I can just multiply them. And this is the trick kind of to prove this thing. So I'm getting it into this form where I want to show that this thing squared is pi, and I have one of them here. The thing I'm going to kind of argue now is that this is actually the same thing as this. So e to the negative x squared is actually what they call the Gaussian curve. If you go and sketch it, you basically get the bell-shaped curve. So you get this kind of thing. This is e to like the negative x squared. And if we think of it in a higher dimension, right? So it's a little hard to draw, but I will attempt here. So maybe this is the x direction and this is the y direction. I basically just get the Gaussian curve in all sorts of different directions. So I can get that one. So I basically am going to get this kind of Gaussian surface now. And you can think of it like over a coordinate axis, and it's sort of just like a mountain in the middle like that. And it doesn't matter which perspective you look at it from. The area under one of those Gaussian curves, whether it's the one that shoots in that direction or one that shoots in like this other direction, the area in those Gaussian curves area under them is the same. And so what I'm basically going to do is just say, well, if the area under this is the area under this, right, they're equal, then I can just kind of jump and say, let x, or y be x, or x be y, it really doesn't matter, but I want specifically x up here. So I'm going to just say, okay, well, these are the same kind of integral, and I'm just going to square my result because I'm multiplying the two of them, right? And we knew that at every point here it equaled pi, right? This thing equaled pi, and then this thing equals pi. And that is what I wanted to show. I wanted to show that if you squared this thing, you would get pi. And it's really just because of the symmetry in those Gaussian curves. It doesn't matter which way you think of it, which is kind of a cool problem.